Assalamualaikum. I am Muhammad Fathah Najee. Today I'm going to talk about fundamental of logic. So what is fundamental of logic? Logic is a way to reasoning that have us make sense of statement and argument using truths of and rules. Let's explore how it works. So our project focus is fundamental of propositional and predict logic, logical operators, and truth table method for evaluating and constructing sound argument. So, what is logic? First, logic is like a toolbox for thinking true or false. There are two main parts in how we understand the logic. First is statement. These are sentences that are either true or false. Like the sky is blue. The true value is tell us a statement is true or false. We also have special tools that is called logical operator. So we have 5 that we learn in this course. First is N. N is the condition. If the condition is true and true, so the both must be true, so that it be true. Then or either one statement is true, not flip the true or false or false to true. And we have if then and if and only if. So we move to the logical equivalence. Next, I'm going to talk about logical equivalence concept, which means two statements that might look different but actually mean the same thing. For example, if I have ice cream, I'm happy, and the second statement is I'm happy if I have ice cream. So I might use the double arrow or triple lines, which mean if and only if. For example, I take from the previous statement, I use A or B and the double arrow, which mean if and only if, B or A. Next, let's look at the example 1. In example 1, we compare A or B and B or A. The truth table show us that both statements are true in the same cases, so they are equivalent. Now let's see the example 2. Here we change the second statement to B or not A. The truth table shows that the results for A or B and C are different from the modified statement. This means they are not equivalent using not that change the outcome. Okay, finally, example 3, we compare A or B and C, and A or B and A or C. The truth table shows that these statements are always the same for the every combination of A, B and C. This means they are logically equivalent.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon everyone. My name is Muhammad Irfan bin Muhammad Zulkifli. So today, I will be walking you through the decision-making logic behind a smart home alarm system. This system is designed to provide a robust and reliable method for detecting potential intrusions. Let's dive into the details of how it operates and the logical reasoning behind its decision-making process. Okay, first, it inputs to the system. The alarm system monitors 3 critical conditions represented by the following inputs. For P, the door is open. Q, the motion sensor detects movement. R, the security camera detects an intruder. Using these inputs, the system evaluates whether to trigger an alert, represented as A. So, when does the alarm trigger? The alarm activates under 2 specific scenarios. First scenario, when the door is open, P, and the motion is detected inside the house, Q. Second scenario, when the security camera detects an intruder, R, regardless of the door or motion sensor status. This condition can be expressed logically as P and Q implies A. That means if the door is open and motion is detected, the alarm triggers. And next, R implies A. If the camera detects an intruder, the alarms trigger. To simplify this logic into a single expression, we combine the 2 conditions. The result is A is equals to P and Q or R. This means the alarm will trigger if either the door is open and motion is detected, P and Q, or the security camera detects an intruder, R. So, for the next steps, we need to verify the logical through equivalence. To ensure the system logic is valid, we use logical equivalence to simplify and verify the expression. By applying the distributive law in logic, we can rewrite the condition as P and Q or R is equivalent to P or R and Q or R. This equivalence shows that the alarm logic can also be understood in terms of a combination of 2 separate conditions. The first one, either the door is open or the security camera detects an intruder, P or R. The second one is either motion is detected or the security camera detects an intruder, Q or R. This alternate form provides additional insight into how the system integrates its input to determine whether the alarm should activate. We also can verify it by using truth table. To further confirm the logical equivalence, we construct a truth table that evaluates all possible combinations of the inputs P, Q, and R. The truth table ensures that the values for P and P or Q and R match exactly with those for P or R and Q or R in every scenario. Let me summarize the key observation. First, when the door is open and the motion is detected, the alarm will activate. Second one, when the security camera detects an intruder, the alarm activates regardless of other inputs. Next one, for every combination of inputs, the 2 logical formulations produce identical results. So the result from the truth table will be equivalent for both equations. This step-by-step verification ensures that the alarm system is logically consistent and reliable. It also highlights the importance of redundancy in security system. For example, if one sensor fails, others can compensate. For example, if the motion sensor doesn't detect movement but the camera identifies an intruder, the alarm still triggers. Then, the logical equivalence also shows how multiple inputs can be combined in different ways to achieve the same outcome. In conclusion, we have seen how the alarm system uses the inputs P, Q, and R to determine whether to trigger an alert. By simplifying its logic into expression A is equals to P and Q or R, we ensure the system is both efficient and effective. Through logical equivalence and truth table verification, we have confirmed that the alarm will always respond correctly to potential security threats.
So, Assalamualaikum to everyone. Today, I'm going to explain to you about the decision-making logic behind a smart sprinkler system. The system is designed to activate only under specific environmental conditions, optimizing water usage and ensuring effective irrigation. So the system evaluates three key inputs, which is P, Q and R. P is when the soil moisture level is low. Q is when the weather forecast predicts no rain, and R, the temperature exceeds a critical threshold. So based on these three inputs, the sprinkler will activate under two conditions. Condition 1 is when the soil moisture level is low, P, and there is no rain in the forecast, Q. The second condition is when the temperature exceeds a critical threshold, R, regardless of the soil moisture level or rain forecast. So these conditions can be expressed using logical formulas. P and Q imply to S. If the soil is dry and no rain is expected, the sprinkler will activate. Second, R imply to S. If the temperature exceeds the critical threshold, the sprinkler will also activate. So by combining these conditions, we simplify the logic into a single expression, which is S equal to P and Q or R. This means that the sprinkler will activate if the soil is dry and no rain is forecast, P and Q, or the temperature exceeds the critical threshold, R. So to verify this logical formula, we use logical equivalence by applying the distributive law. We can rewrite the expression as P and Q or R equivalence to P or R and Q or R. So this alternate form divides the decision making into two separate checks, which is either the soil is dry or the temperature is too high, P or R. And then the second one is either no rain is forecast or the temperature is too high, Q or R. So next, we will confirm this equivalence with the truth table, analyzing every possible combination of the inputs P, Q and R. The truth table clearly shows that the two expressions, which is P and Q or R, and P or R and Q or R, produce identical results in every scenario. This verification ensures that the system logic is accurate. Lastly, to conclude it all, the smart sprinkler systems will only activate when necessary, based on the conditions of soil moisture, rain forecast, and temperature. The logic ensures that the water will be used efficiently, triggering the sprinkler only in cases of dry soil, high temperature, or both. By verifying the logic with equivalence and the truth table, we can confirm that the system is both reliable and effective. This decision-making approach not only optimizes water usage but also adapts to varying environmental conditions, making it an intelligent addition to any irrigation setup.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adam Rahimi bin Rosli. So, we go to the next subtopic, which is rules of inference. So, here the common rules of inference. There have 7. Right. So, we will gain more knowledge about rules of inference. I will give the meaning of each rules and example. So number 1, modus ponens. If P is true, then Q must also be true. The example, if it rains, the ground will be wet. So the P is it rains, then the Q, the ground is wet. So number 2 is modern tolerance. If Q is false, then P must also be false. The example, if the light is on P, the room is bright Q. So the room is not bright, not Q, therefore the light is not on, not P. So number 3 is hypothetical syllogism. If P implication Q and Q implication R, then P implication R. The example, if I study P, I will pass the test Q. If I pass the test Q, I will graduate R. Therefore, if I study P, I will graduate R. We will go to number 4 rules, which is disjunctive syllogism. So if one input is false, then the other must be true. The example, either the train is late P or I miss its Q. Alright, so the train is not late, not P, therefore I miss it, Q. Alright, so number 5 is conjunction. The meaning that I can give, if both statements are true, we can logically connect them with and. Alright, the example that I can give is I ate breakfast P, I drank coffee Q. Therefore, I ate breakfast and drank coffee, which means P and Q. The next rule is simplification. If a combined statement is true, we can simplify it by focusing on just one part of the statement. The example, I study and I pass the test P and Q. Therefore, I study P. Alright, the last rule is addition. If one statement is true, we can add another possibility to it using or. Even if the second part is uncertain or false. The example, I study P. Therefore, I study or I went to the movie, P or Q. We will walk through a scenario where logical rules are applied to understand when an alarm system gets triggered. By using the premise provided, we can logically determine when the alarm activates based on certain conditions. So, there have 3. P, the door is open. Q, the motion sensor detect movement. R, the security camera detect an intruder. So, the alarm is triggered when it go to condition. Condition 1, if the door is open, the motion sensor detects movement. So, it will be P and Q. Condition 2, if the security camera detect an intruder. As the result, the condition for the alarm to trigger is A equal P and Q or R. Okay, so we will solving the situation using rules of inference. So step 1, we assume P and Q. We start by assuming the both P and Q is true. Since both are true, we combine them using the conjunction rule. It will be result P and Q. This establish the first possibility for triggering the alarm. Okay, step number 2 is derive A equal P and Q. Since we know that P and Q are true, we can simplify the overall alarm condition A equal P and Q or R to conclude that the alarm is true if P and Q is true. So, we can state that P and Q implication A. The next step is assume R. So, we will make R is true. Using this assumption, we can state that R alone enough to trigger the alarm. This satisfies the second part of this disjunction A equal P and Q or R. As the result, we have R implication A. The last step is combine cases with disjunction introduction. From step 2, we know that P and Q implication A is true, and from step 3, we also know that R implication A is also true. We can conclude that the alarm can be triggered in either of the following cases: A equal P and Q or R.